All right, let's dive in. Today we're talking about an absolutely massive engineering challenge. I want you to picture a structure that's taller than a skyscraper, but it's floating in the middle of the ocean, generating power while constantly getting battered by wind and waves. This is the wild world of floating offshore wind turbines, and we're going to figure out how they possibly survive out there.
And that really is the core question, isn't it? How on earth does something so enormous, so incredibly top-heavy, not just tip over in a restless sea? It's a fantastic puzzle of physics and hardcore engineering.
So first, you've really got to wrap your head around the scale we're dealing with here. These are not just windmills on some kind of boat. We're talking about colossal structures that are built to operate in one of the most hostile environments on the entire planet. Okay, so to understand how these survive all that, we've got to go back to basics. We have to start with the fundamental balancing act that lets anything float in the first place.
It all starts with a simple push and pull. You've got the immense weight of the entire turbine, gravity, pulling it down. And at the same time, you've got the force of buoyancy, which is just the water pushing right back up. When those two forces are perfectly balanced, hey presto, the turbine floats. Simple enough, right? Well, that is just the very beginning of the story.
But what happens when a wave comes along and tilts the whole platform? This is where a pretty cool concept called hydrostatic restoring moments comes into play. It's all about the shape of the platform. See, as it tilts, the center of buoyancy shifts, and that creates a restoring moment. Basically a natural built-in tendency for the platform to push itself back upright. Think of it like one of those inflatable punching bags you had as a kid that you just can't knock over. Okay, so the turbine can float and it can right itself, great. But now, let's introduce the chaos. Let's talk about the wind, the waves, and the water that are constantly trying to throw this thing off balance. First up, the most obvious one, the wind. But the wind does a whole lot more than just spin the blades to make power. It exerts an absolutely incredible amount of force on the entire structure. So the most important force here is something called thrust. It's this constant, massive push on the giant rotor, way up high above the water, and this creates what engineers call an overturning moment, which basically means it's the number one force trying to topple the whole turbine over. It's pushing the top while the bottom tries to stay put. But the wind isn't the only thing attacking it. The ocean itself is constantly pushing and pulling on the submerged part of the platform. These are the hydrodynamic forces, and they are absolutely relentless. And you know, the water plays this fascinating double role. On one hand, you've got wave excitation. That's the waves constantly lifting, dropping, and shoving the platform around, making it bob and sway. But on the other hand, the water also creates viscous drag. That's kind of like friction, and it actually helps to slow down and dampen those exact same motions. So it's a constant push and pull, with the water being both the problem and part of the solution. And you'd think that would be enough to deal with, right? Nope. The complexity doesn't stop there. Beyond the obvious push of wind and water, you have to account for some unseen forces happening inside the turbine itself. This is where things get a little weird. Because that massive rotor is spinning with incredible momentum, it acts like a giant gyroscope. And what this means is that forces don't always behave the way you'd think they should. A push in one direction might not just move it that way, it could cause a twist in a completely different direction. This means that a simple yawing motion, that's just turning left or right, can actually create forces that make the turbine pitch forward or roll side to side. Engineers have to account for this bizarre coupling of forces to keep the thing stable. It's like a game of three-dimensional chess out there. But here's the thing, the turbine isn't just a passive victim in all of this. It actually has a brain. The control system is constantly making these tiny adjustments to the pitch of the blades and the torque of the generator. It's actively fighting back against the wind, both to maximize the power it's making and, crucially, to reduce all the stressful loads on the entire structure. So, with all these competing forces, the wind, the waves, the weird gyroscopic effects, the control system, how do you engineers predict and control this incredibly complex dance? How do you design a machine to operate in what is, for all intents and purposes, a controlled hurricane? Well, the answer, believe it or not, comes down to a single number, 6. To get a handle on the chaotic motion of the turbine, engineers break it all down into 6 fundamental movements. These are known as the 6 degrees of freedom. You've got 3 linear movements, surging forward and back, swaying side to side, and heaving up and down. And then you have 3 rotational movements, rolling from side to side, pitching forward and back, and yawing left and right. Every single possible motion of that turbine is some combination of these 6. And that brings us to the final crucial piece of the puzzle, the one thing that stops the turbine from just floating off to another continent, the mooring system.
And these aren't just simple ropes. They are a highly sophisticated engineering system that holds everything in place.
This mooring system has two critical jobs. The first is position keeping, which is pretty self-explanatory. It's the giant anchor fighting against that horizontal surge and sway. The second is providing stability. It adds stiffness and damping to the entire system, helping to counteract the roll and pitch. It is the turbine's fundamental connection, its lifeline to the Earth.
So the next time you see a floating wind turbine, you're not just looking at a machine, you're looking at the result of this incredible balancing act, a constant, chaotic dance between the raw forces of nature and some truly remarkable engineering. And it leaves you with a big question, right? Is mastering this kind of controlled chaos the key to our clean energy future?